I'm Adam Keiper, editor of Big Questions Online. In January 2017, I attended a conference in Washington, D.C., held by the American Physical Society to hear a lecture by Martin Rees, one of the world's most prominent astrophysicists and cosmologists. Lord Rees is a former president of the Royal Society and has, for more than 2 decades, been the Astronomer Royal. He has received numerous awards, including the Templeton Prize, in recognition of his contributions to astronomy and cosmology, which include research on black hole formation and on the cosmic microwave background, a key piece of evidence of the Big Bang. He's also written several popular books about science. Lord Rees's lecture provided an overview of what cosmologists believe about how the universe as we know it came to be. He touched on the Big Bang, redshift, background radiation, and dark matter, and dark energy. He also ventured into more conjectural domains to consider multiverse theory and string theory, and whether the universe might end in a big crunch or a big rip. He emphasized the distinction between well-established cosmological theories and what he calls speculative physics, as well as the limits of what we can know about the observable universe. The next day, Lord Rees sat down with me and a BQO camera crew over lunch to chat about some of the big questions he addressed in his talk. How big is the physical universe?
Well, the universe we can observe extends out to very distant galaxies, which we are seeing as they were about 11 billion years ago. And there is a sort of horizon, because however powerful our telescopes are, we can really never see beyond a certain distance, which is in effect the distance of the galaxy that first formed, because as we look further away, we're looking back in time. So the observable universe is huge, of course, but it's still finite. And there's a horizon around us, a sort of shell, beyond which we could never, in principle, make observations, because, as it were, light's never had time to get to us from beyond that shell since the Big Bang. And that is important as a horizon of observations, but it has no more physical meaning than the horizon around you if you are on a boat in the middle of the ocean. And just as in that case you don't think that the ocean necessarily stops just beyond your horizon, so there's no reason to think that galaxies stop before we get beyond that horizon. And indeed, there are fairly strong reasons to think that galaxies go on probably thousands of times further. The reason for that is that if you look at all the galaxies in one direction and then in the opposite direction, the difference between their properties and their spatial density is less than 1 part in 100,000. So if we're in some huge finite structure, the gradient across the region we can look at is very small, and that therefore suggests that it's a structure much, much bigger than the little domain that we can observe. So I think most people would say that the universe goes on 1,000 times further, but that's just a lower limit, and it could go on forever. Certainly so far even that all combinatorial options would be fulfilled if there's enough space.
So connect that idea of the universe going on and fulfilling all the combinatorial options with the multiverse theory.
Yes. Well, we can in principle imagine that the aftermath of our Big Bang goes on almost forever, to an extent so large if we get combinatorial options. But that's not all, because our Big Bang may not be the only one. And there are lots of quite well-formulated ideas dating back 30 years which suggest that if the physics of the early Big Bang has certain properties that we can specify, although we can't test, then we will get a Big Bang which spawns a whole lot of progeny, as it were. We get what Andre Linde calls eternal inflation. And so our Big Bang, which has an aftermath far larger than the domain we can observe, may in itself be just one island, one oasis in a huge archipelago of other space-times. So that's the idea of the multiverse.
About 10 years ago, I was on a panel at Stanford where we were asked how much we'd bet on the multiverse concept panning out. I said that on the scale, would you bet your goldfish, your dog, or your life? I was nearly at the dog level. Andre Linde, who'd spent 25 years on eternal inflation said he'd almost bet his life. And later on being told this, Stephen Weinberg, the great theorist, said he'd happily bet Martin Rees's dog and Andre Linde's life. Well, Andre Linde, my dog, and I will all be dead long before this is settled, but it's not metaphysics. It's speculative, but it's exciting science, and it may be true.
You spoke yesterday about an area of physics that was speculative physics. The multiverse theory fits, I would say, pretty squarely in speculative physics.
Yes.
And that raises some interesting questions about how one would ever verify multiverse theory. And you suggested that one way that we might do that is if multiverse theory allowed us to make any predictions about things that we don't already know about the nature of our own universe.
Yes.
Could you say a little bit more about that?
Yes. Well, if we think of our standard picture of the Big Bang, which of course we didn't have in the middle of the 20th century, we now can extrapolate with fair confidence back to when the universe had been expanded for just a nanosecond, because we understand the physics back to that time. That was the time when the particles moving around with an energy like we could produce an accelerator. So we can extend back with great confidence to 1 second, because that's when helium was made, and we know the abundance of helium, and back to a nanosecond with reasonable confidence. But if we want to understand key features of the universe, like why it's expanding the way it is, why it's got this particular content of dark matter, atoms and radiation, we need to go back further still. And for many reasons, it's thought we have to go back a huge distance further to a time when the universe had been expanding for a trillionth of a trillionth of a trillionth of a second. And the physics then was much more extreme, because the observable universe, which would be the size of a solar system as a nanosecond, would be literally that big at this time. So it's a huge extrapolation. And so before we understand the physics of that time, we need some big breakthroughs. And of course, people are working on unified theories that unify the physics of the very small with the physics of the very large, quantum gravity, etc. And if we had a theory like that, then it would apply to these very early stages. Now, you have to then ask, how would we ever test that theory? And I think no one's going to take seriously a unified theory unless it has tests as you can do in the lab or in the everyday world. But if we had such a theory, and if it, for instance, told us why there were 3 kinds of neutrinos, what the masses were, why the constants had the values they did, and maybe predicted other things, then that theory would gain credibility. And then we would take seriously its other predictions, even if those other predictions can't be directly verified. To take an example, we take seriously what Einstein's theory predicts about the inside of black holes, which we can't observe, because we've confirmed Einstein's theory in many other contexts, outside black holes and in the solar system, etc. And so we may, within the next 50 years, have a theory which applies to the very early inflationary stage of the universe, which has been, as it were, battle-tested by being vindicated by observations in the everyday world. Okay? And then the question is, does that theory have the properties which Andre Linde's multiverse model demands, or not? We've no idea. We've no idea whether we have this theory ever, but if we did have a theory, and if it had the properties which were consistent with some of these ideas of the early Big Bang that lead to a multiverse, then we would take that prediction seriously. And as I said, we know that with reasonable confidence that there are galaxies beyond our horizon, unobservable galaxies, and I think even the most conservative astronomer is happy to assign reality to galaxies which are beyond our horizon, then I don't see why those should have higher epistemological status than galaxies that are the outcome of other Big Bangs.
First, are there many Big Bangs or just one? Second, if there are many, are they all governed by the same physics or not? According to string theory, there could be a huge number of different vacuum states, different values of lambda, different microphysics. And if that theory were right, what we call the laws of nature would, in this grander perspective, be, as it were, just local bylaws governing our cosmic patch.
You mentioned string theory here just now. You mentioned string theory last night.
Mm-hmm.
Many people have a vague sense of what string theory is. Many people have a vague sense of what multiverse theory is from the popular accounts of each of these, without having a real grasp of what the science is or of any of the equations. How would you explain to a general audience what the relationship is between string theory and multiverse?
Well, I say string. Well, as I say, one of the challenges for 21st century science is to reconcile the physics of the very small, which is quantum physics, with the physics of the very large, which is Einstein's theory of gravity. This is irrelevant to most of science, because if you're thinking about small things in the everyday world, then you don't need to think about gravity and quantum at the same time. But if we want to think about the Big Bang, when everything was squeezed to microscopic size, you clearly need a theory that reconciles these two. And there are many different quests being followed for such a unified theory. String theory is the best known, but there are others. But I think the one thing that everyone does suspect is that to actually come up with such a theory will involve a leap down to much, much smaller scales. There's a particular scale in physics which is called the Planck scale, which is a trillion times smaller than any scale we can now measure. And that is the scale when quantum fluctuations are such that they give rise to black holes. If you imagine a black hole getting smaller and smaller, it gets less and less massive, but the quantum uncertainty in its position gets larger and larger. There's a certain scale where those two overlap, when the quantum uncertainty in the position of something is equal to its size. And that's the so-called Planck scale. And most theorists, whatever they think about string theory or other theories, they would suspect that if you chop up space into very tiny units, you get down to a stage where it's more complicated. If I take this table, I can chop it up, but I can't chop it up small on an atomic scale. Similarly, it's thought that you can't chop up space and time into arbitrarily small units, but the scale down to which you can chop it up is the so-called Planck scale, which is 10 to the minus 33 centimeters, which is a trillion times smaller than an atomic nucleus. And that is a scale where almost certainly quantum theory and gravity meet. And according to string theory, if you were to look at a point in space with that magnification, you'd find that it was actually a tightly wound origami in 5 extra dimensions. We don't detect those because they are wound up on that scale. So the texture of space itself, in most of these theories, is so tiny that we don't directly observe it. But that is the sense in which we have to make huge progress in order to have a theory that unifies gravity and quantum theory. And that same theory will, of course, be necessary if you want to really understand the early Big Bang.
Until 50 years ago, we didn't have firm evidence for a Big Bang. Now we know a lot about its properties and how it's led to the cosmic panorama of which we're a part. So 50 years from now, there could be a theory of 10 to 16 GeV physics that gains credibility and that predicts a multiverse and in principle determines some of its properties. Well, some don't like this multiverse idea at all. It would render the hope for neat explanations of the fundamental physical numbers as vain as Kepler's numerical quest to understand the solar system. But our preferences are irrelevant to the way physical reality actually is, so we should surely be open-minded.